What you're hearing is synthesized entirely from scratch. It runs procedurally, and I can control many characteristics of the water, such as the density, tone, and acoustics. In this tutorial, I'll break down my process for synthesizing flowing water and similar sounds like rain. Sounds like water splashes will not be included in this video, though I may explore it in the future. To start, we need to look at recordings of water. Specifically, it's important to understand how the sounds are layered. To effectively replicate water recordings, it's necessary to analyze them. Generally speaking, they can be broken down into frequency bands. This will be important later when sound designing, as controlling different bands will change the shape of the sound, allowing you to mimic various water sources such as rivers and rain. Another characteristic of many recordings is the presence of background noise. Synthesizing a simple and controllable noise floor can imitate different recording styles and environments. To simplify the process, I usually analyze recordings in 3 bands: lows, mids, and highs. We can compare the density of each band between recordings and make notes about them for our synthesized water. Patterns in loudness, frequency distribution, and droplet length are important to observe. Once you've analyzed some recordings, you can set up the sound design process, starting with the MIDI input. The MIDI input is important as it will allow you to control the droplet impulses without having to worry about them too much in the actual synthesis stage of your sound design. For flowing water, my MIDI chain generally looks like this. First, I have a legato input, in other words, a sustained note inside a MIDI clip, then arpeggiation, note density, basically just some way to control the amount of impulses, and lastly, MIDI echoes, which serves as a method to layer impulses quickly. I'll be using Ableton Live 12, however these concepts should be applicable across most DAWs. Starting off, while this step may look different for disparate systems, for mine I simply start with the legato note. The length of the note will determine how long the water sound generates. At the beginning of my MIDI chain is an arpeggiator. I randomly modulate the rate to trigger random note timings. Depending on how you create the envelope for the droplet later on, you may be able to use the gate parameter to control note lengths. Additionally, if your input is polyphonic, you can try using different arpeggio styles. Preceding the arpeggiator is a good place to introduce a way to control density. By density, I'm referring to how many notes actually come through. Thus, a parameter that controls the probability of notes occurring should work. For this, I'm using a simple rack created by my friend 2L. It works by controlling the input velocity with some velocity devices. The last part of the MIDI chain consists of MIDI echoes. These devices make the incoming notes echo as MIDI notes, sometimes with the option to vary the pitches of the echoed notes. For Ableton Live, there are a few free devices out there for this, such as NoteROM and NoteEcho. For variation, I perform random modulation on the echo timing in milliseconds and the echo velocity. Furthermore, I modulate the feedback with a square LFO so that the echoes are not constantly piling up, which can lead to some noticeably synthetic sounds. I also modulate the echo's pitch, however, you can use the random device as an alternative. This stage can change the result quite a lot. so try to experiment with multiple MIDI effects. Once the MIDI chain is set up, it's time to begin synthesizing the water. The sound of flowing water is the product of many complex factors, including droplet impacts, water turbulence, the dimensions of the water, the speed of the water, and the acoustic properties of the surrounding space. The simplest of these sounds is the plink sound generated by water droplets. When a droplet impacts a liquid surface, it creates a cavity on the surface while sending an underwater air bubble, a process known as bubble entrainment. Theoretically, this bubble then disturbs the cavity on the water's surface, which is a major source of the airborne sound. As the bubble rapidly shrinks, the frequency of the sound increases, so we need to mimic this pattern with pitch modulation. Other factors for the pitch and loudness of the sound include the droplet's size, impact velocity, the dimensions of the water it's falling into, and more, which you can incorporate in your sound design depending on how detailed you want it to be. You can start synthesizing the droplet sound with a simple pure tone. This is where you should reference the amplitude envelope and initial frequency of a real droplet sound. Once you've set those parameters, you can modulate the pitch with a curve resembling your reference droplet's pitch curve. Of course, you need to create variety when emulating natural sounds like droplets. To do this, reference a larger set of droplet sounds. Then, you can randomize the initial pitch, loudness, length, and pitch curve of your droplet, matching the range of variation in your reference set. For randomizing the initial pitch, you can either use the random device in the MIDI chain, or you can use LFO shapes like random or sample and hold. In addition to all of this, you can introduce even more variation by randomly modulating resonant high-pass filters. Even if the input is just a sine wave, randomly moving high-pass filters while the sine wave changes in pitch can create subtle differences. Furthermore, because droplet sounds often have this transient burst of noise, you can create a noise transient in parallel with the droplet. Once the individual droplets are synthesized, we can extend these concepts to start generating the flow of the water. We can integrate the MIDI process discussed earlier with our droplet synthesis to generate a more consistent flow. This is where you should especially study water recordings, as the parameters you set up for your droplet synthesis will vary. First, we need to effectively layer the sound. For my system, I have 9 chains generating droplet sounds in parallel. Each chain operates in a different frequency range. My chains generally follow the preceding process. First, I have the MIDI process as discussed earlier. Then, I have the synthesized droplet, which is unique for each chain. I try my best to mimic the droplet sounds of the frequency range I'm analyzing, and I primarily use faceplant or Ableton's operator. Following the droplet generation, I have a modulation group. This is a group of modulators that modulate any parameters that aren't being modulated within my droplet synthesis patch, which could be EQs, delays that come later in the chain, and more. Next, I have EQs that isolate frequency ranges to make sure that the droplet sounds roll off near the ends of the range. I then have a feedback loop. This is not as practical as the other steps, as this step is more for creative control. It follows a technique I learned by my friend Maluk, whose channel is linked in the description. It works by creating a feedback loop with ring modulation. Specifically, a ring mod precedes a group of multiple effects, such as delay. The output of the group is then fed back into the ring modulation, where I then use the bias parameter as a way to control the amount of processing. I found that this process has made the chain sound a lot more dense and interesting. Finally, I have a group for mixing, which is just an assortment of EQs, stereo processing, and resonance suppression. Again, I have 9 of these chains running in parallel for different frequency ranges, which are as follows. The first 3 chains are for the high end, ranging from 2 kHz to 16 kHz. The next 4 chains are for the mids, ranging from 250 Hz to 2 kHz. The last 2 chains are for the lows, ranging from 25 Hz to 250 Hz. I technically have a 10th chain, however, this is for background noise. How many chains you have generating droplets will depend on the water style along with your CPU load. Because the MIDI generation can be CPU intensive, I have a method for creating density in post, which I will explore later in this video. For each chain, it's good to reference the properties of water recordings within the intended frequency range, and match the density and other characteristics of your synthesized water accordingly. This process can be time-consuming and a bit frustrating, so be as patient as you can with it. To shape the tonality of your water, you can use the density parameter that was discussed earlier, which should be in each chain. This will allow you to independently control the amount of droplets generating within each frequency range. Now that we've explored the process for generating flow, we should understand how it may differ for different water sound sources, such as waterfalls and rain. When you're sound designing disparate water systems, analysis should again usually come first. An important noise to compare between water recordings is, well, noise. While I've mentioned background noise, there's another kind of noise which comes from the water itself. While the factors behind water spectra aren't as researched as you might expect, turbulence alongside water collisions with the environment seem to contribute greatly to the intensity of the noise, and more precisely, the slope of the noise over the frequency spectrum. So, with more turbulent water systems, like rapids and waterfalls, we can inspect the ratio between the noise and more discrete bubble sounds. As a rule of thumb, we can say that the more chaotic the water system, the more noisy and less distinct the sounds will become. Thus, with waterfalls, you can start by generating white noise and following the slope and characteristics of waterfall recordings using filters and other effects. This same noise layer is also present in rain, which is the result of countless droplet impacts. The ratio between the noise and discrete droplet sounds, which we can call the signal-to-noise ratio in this case, will depend on where you are imagining your microphone to be. If you are recording near a hard surface, for example, you could expect a higher signal-to-noise ratio, or in other words, more noticeable droplet sounds. Here is an example of synthesized rain using those concepts along with my droplet and noise synthesis. With the synthesis out of the way, we can now move on to getting the sound to feel more full and realistic in post. After I had released my biota tutorial about sound designing ecosystem soundscapes, the creator of MyNoise, a website allowing you to customize soundscapes, reached out to me for an adaptation of biota as a customizable soundscape on the website. However, because the water sounds in biota were the only thing not designed completely from scratch, given they partially utilized granular synthesis of real recordings, I offered to send over some fully synthetic water. When I had sent it over, he had an insight that was effective yet simple. He noted the water sounded great but singular, and so he processed it by stacking the same audio file many times, but with each instance having different start offsets and pitch variations. This resulted in the water sounding far more dense and complex. Furthermore, since this is done with minimal audio processing as opposed to more intensive procedures like MIDI generation and synthesis, it's quite CPU efficient. Thus, I've used this idea for the water sound design you hear in this video. If you want to check out the My Noise adaptation of Biota, there's a link in the description. Anyway, my method for stacking in post is as follows. Preceding my water generation chains, I create a group with several chains in parallel, essentially stacking the audio several times. You should probably do some kind of gain compensation for this, as it can get loud fairly quickly. In my case, I adjust the volumes of each chain however I see fit. At the start of each chain is a delay that shifts the start position, making sure that each instance is offset differently from one another. Then, I perform some kind of pitch manipulation or unique processing, which could be done with pitch shifting, frequency shifting, or other creative effects. I have the parameters set differently for each chain to ensure they're not sounding too similar or obvious. This process of course makes it take longer for your sound to start generating properly, as the stacking involves delaying the audio by different amounts. However, I think the result is pretty worth it. Once you've set up your stacking system, we can finally move on to the last step, the acoustics. Even if your synthesized water sounds great on its own, it still won't sound nearly as realistic as it could without considering the acoustics or surrounding space. Technically, some of what I've discussed already relates to water acoustics, but here I specifically want to explore reverberation, distance, and more. In my project, I mostly used the free Max for Live device ml.distance along with additional filtering to emulate distance. Even if you're not using Ableton, the idea is just that the more distant a sound is, the less high frequency content, as higher frequencies tend to attenuate more so than lower frequencies over distance. Furthermore, the overall signal becomes quieter and the source loses stereo width. There are, of course, more nuances in the propagation of sound, such as temperature, humidity, an environment's geometry, and more, which you can research to make your system a little more realistic. For reverberation, I recommend using convolution reverb, possibly even in conjunction with algorithmic reverb. If you're using Ableton, hybrid reverb is great for this. I like using a combination as I have more control over algorithmic reverbs, allowing me to shape the space, but I also use convolution, so that I can have impulse responses of some desired environments as well. With all that being said, I also experimented around with a more unique and interactive reverb plugin, called Room 360, which isn't yet released. However, I will link the creator's channel below as this plugin is pretty awesome. Finally, I have one other pretty cool technique for emulating recording styles and acoustics, though it's not as accessible. If any of you watching have Pianoteq 8, which is a plugin that physically models pianos and some other instruments, you can actually use it for your water synthesis. In short, you can send your water tracks output to Pianoteq using the sidechain input of Pianoteq. And since Pianoteq actually simulates the sound field generated by an instrument, you can take advantage of this by running your water sound through the soundboard model, which will then be simulated in the sound field. The results can get pretty bizarre depending on the instrument model, but here are a few examples of this with some different microphone techniques. So that just about covers everything, but I want to make a couple notes before I wrap up the video. Sound design can be very difficult, especially when designing natural sounds. Thus, iteration is very important. I had lots of frustrating moments during this project and went through many versions before I got a sound I was happy with, so be as patient as you can. If you wish to support my work, you can do so on my Bandcamp, linked in the description. Alternatively, you can also leave a super thanks in the comment section, as your support allows me to create these videos. I make these videos not just to explain specific sound design concepts, but to inspire people to explore sound in their own ways. If any of you have synthesized your own water, feel free to explain your process and experience in the comments. Thanks for watching.